Our next lesson is about the Side-Splitter Theorem and focuses on Module 2, Lesson 4. In this lesson, we cover one CCRSM standard to prove another theorem about triangles. In this one, we're proving a line parallel to one side of a triangle divides the other two proportionally. Now, you might remember that back we did a lesson about mid-segments, where if this is the midpoint and midpoint, then the mid-segment is half as long as the third side. Remember that? Well, this is more of a generalization of that idea, whereas as long as it's parallel, then this side, then this ratio is the same as this ratio. There's not really a standard way of marking sides to be proportional, but what it's saying is that if these lines are parallel, then these are proportional to these sides. Okay, now that's very much connected to the ratio method and the parallel method, and so we'll be proving how one implies the other and vice versa. Let's get started. Now, before we get into the proof of the Side-Splitter Theorem, there are two opening exercises that we have to go through because the proof uses these ideas. The first is we have two triangles, triangle ABC, which I've drawn in red, and triangle ABD, which I'll draw in green. Both have base AB, and points C and D lie on a line parallel to AB. Show that their areas, meaning the area of the red triangle and the area of the green triangle, are equal. Well, I know that to find the area of a triangle, it's equal to 1/2 base times height. And the base of the red triangle, ABC, is AB, and the height is right here. Now I'll make a new point, I'll call it point C prime, but the altitude or the height of that triangle is CC prime. Now I'll go over to the green triangle, is also 1/2 base times height. The base is also AB. And now the most important thing of this exercise happens, noticing that because CD is parallel to AB, that this altitude right here is the exact same for D. So I can use the exact same altitude because it's the same height for that triangle as well. So this is also C prime. And then we notice, hey, these are the exact same. And so what that means by substitution, that the area of triangle ABC is the same as the triangle for ABD. So it's important you notice that if we have two triangles with the same base and their third point is on a line that's parallel to the base, then those two triangles will have the exact same area. We'll need to use that in the Side-Splitter Theorem proof. The second idea that comes into play has to do with this down here. Suppose two triangles have different length bases. So here I have a triangle where the base is AB in blue, and I have a triangle with length AB prime, which is in green. And my goal is to show that those two, the areas of those triangles, have the same ratio as the ratio between those lengths AB and AB prime. To show this, we'll look at the area of triangle ABC and the area of triangle AB prime C. The area of triangle ABC is 1/2 base times height. The base is still AB, and the height is right here. So I draw an altitude just like I did before, and I'll call this point C prime. And the height of triangle ABC is CC prime. Now I will pause right there, and I will go and find the area of AB prime C, which is drawn in green. It is also 1/2 base times height. The base is AB prime, and the height is also CC prime. Now, if I take these two equations and plug this in here and plug this in here, then I will show that the and by canceling off, as I'm dividing, I can cancel off things. I find that AB over AB prime. So what that means is that if they have the same altitude but different bases, then the area of the two triangles is the same as the ratio between the side lengths. All right, we will use those two ideas as we prove the side-splitter theorem. Last lesson, we looked at two ways of drawing scale drawings. We started off with the ratio method where we found this length and multiplied it by a scale factor and got this length. And then using the same scale factor, we took this length and multiplied by that scale factor and got this length and found the scale drawing. This is called the ratio method. The other method we used, which was called the parallel method, we would use the ratio method for only one of them, take that length times the scale factor to get this one, but then I simply construct a line parallel to this one, and wherever it intersected here is where it should be. Now in our proof today, we are simply going to prove that these two are equivalent, that the ratio method is the exact same as the parallel method, and the parallel method is the exact same as the ratio method. We will start off with proving that if you have the parallel method, then it follows that the ratio method must be true. So in this theorem, we are given AB and point O not on segment AB, and we construct a scale drawing of AB with scale factor r greater than 0 using the parallel method. So A prime is the point I get after dilating A with center O and the scale factor of r. And then I use parallel lines to see where it intersects with OB, with ray OB, and that this point B is where it intersects. And my goal is to prove that that's the exact same point I would have gotten if I would have used the ratio method. Okay, here's the proof of that half of the theorem. We will prove the case when r is greater than 0, just for the picture, but we could prove the case where r was between 0 and 1 the exact same way, but with a slightly different picture. Construct two line segments, BA prime and AB prime, to form two triangles, BA B prime, which I've drawn in green, and BAA prime in blue. And they're labeling those as T1 and T2. So the green one is T1 and the blue one is T2, respectively, in the picture below. Okay, now while I'm sitting here in this picture, let me show you that using the first exercise we did, notice that these are parallel and they have the same base. And so from what we showed you earlier in this video, the very first exercise, that means that the area of T1 must be the same as the area of T2 because they have the same base and altitude. So the next says the areas of these two triangles are equal. The area of T1 is equal to the area of T2 by exercise 1, the first thing we saw. We'll next label triangle AOB, this, T sub 0, and we will talk about area of AO prime B and the area of AB prime A, and they must be the same because down here this blue triangle is equal to T sub 0 plus T2, and the green triangle down here is equal to T sub 0 plus T1, and we just proved that T1 and T2 were the same, and so those two triangles must be the same. That's important for us later on. Next, we're going to use the idea in exercise 2 that had to do with the same altitude but different bases, and so we got a similar, a proportional area as that length. We're using that idea on two sets of triangles. TO, so this triangle right here, we draw it in black actually. T sub 0 is this triangle right here. And OA prime B down here. So notice that these both have the same altitude, but they have a different length down here, different base length. And so by the second exercise earlier, I know that the ratios of these must be the same as the ratios of the bases. Similarly, for TO, the same TO, and triangle OB prime A, this green triangle, that because these have the same base, meaning OB, that the area, that the ratio between these is the same as the ratio between OB and OB prime. Now please remember that earlier we proved that the area of triangle OA prime B is the same as the area of OB prime A, and the area of T sub 0 is the same as itself. So the left sides of both equations are equal, and so by substitution, I know that OA prime over OA equals OB prime over OB. That's written down here. And also, we started off with defining the ratio R, the scale factor R, by being what OA prime over OA was, and therefore OB prime over OB must be the exact same as R. Or if I rearrange that by multiplying both sides by OB, I get this equation, which is what I would have gotten if I used the ratio method. So that long proof showed that if I use the parallel method, I get the exact same point as I would have gotten if I would have used the ratio method. Next, we will prove the inverse of that, meaning if I start with the ratio method, I will get the exact same point I would have got if I would have used the parallel method. This time I will just start with the proof. Since both the ratio method and the parallel method start with the same first step in setting A prime is equal to the point I get after dilating point A with a center of O and a scale factor of R, the only difference between the two methods is how the second point is found. If we use the parallel method, we construct the line L parallel to AB that passes through point A prime and label the point where L intersects OB by C. So if we use the parallel method, which we just did earlier, and got this point, which in this version they're calling it that point C, then B prime is the same point found using the parallel method if we can show that C is the same as B prime. So if I can show that those are the same point using the ratio method down here or the parallel method, then that's what I need to show. By the parallel method to the ratio method theorem, which I just did, we know that C is equal to the dilation I get when dilating point B with the center of O and scale factor R. But B prime is also the point on OB such that OB prime equals R times OB, right? So this is what I get from the ratio method, so they must be the same point. So I've now proved this theorem both ways, that if I start with the parallel method, I get the exact same thing as I would have used with the ratio method, or if I use the ratio method, I get the exact same thing as the parallel method. Now these two ideas together is often stated as called the Side-Splitter Theorem, which says a line segment splits two sides of a triangle proportionally if and only if it is parallel to the third side. Now we've not used the phrase if and only if very much in this class or talked a lot about that phrase. What that means is I can break this statement into two other statements. One is if a line segment splits two sides of a triangle proportionally, then it is parallel to the third side, which we proved. We can also say within this if and only if that if a line segment is parallel to the third side, then it splits two sides of a triangle proportionally. And we proved both of those earlier in that proof. So those two ideas are both combined in this phrase, if and only if. So here's one quick example of the parallel theorem, of the side-splitter theorem in action. If we are given that AC is 12, and AB is 6, and BE is 4, and these angles are the same, then find CD. Now, if these are equal to each other, then these lines must be parallel because they're corresponding angles. So I can use the side-splitter theorem. And so if I call this X, then I know that these are proportional to these sides. So 12 over X is equal to 6 over 4. Those are proportional. And I can solve that by cross-multiplying. X times 6 is 6x. 12 times 4 is 48. I divide both sides by 6, and x is equal to 8. That's the side splitter in action. But keep in mind that our theorem wasn't to use the side splitter theorem. Our standard said to prove the side splitter theorem, and we'll focus more on that during class. This video was about the side splitter theorem and proving the side splitter theorem, which is that a line parallel to one side of a triangle divides the other two proportionally. Thank you so much for watching.